Imagine you're in your bedroom using your phone. The Wi-Fi signal passes through the walls and everything works normally. But if you shine a flashlight at the same wall, the light doesn't make it through at all. That's strange, because both Wi-Fi and visible light are electromagnetic waves. So why does one pass through the wall while the other doesn't? Let's investigate. Both waves are meeting exactly the same wall. The distance is the same, the material's the same, yet one wave reaches the other side while the other doesn't. Something important must be happening inside the wall. If you've searched online before, you've probably heard a simple explanation. Wi-Fi has a longer wavelength. While that's true, it doesn't tell the whole story. Let's test that idea. If wavelength alone explained everything, why does metal almost completely block Wi-Fi? Why does thick concrete reduce the signal? And why does visible light pass through glass so easily? Clearly, there's more to the story. Today, we're going to uncover what that missing piece is. Instead of asking, why does Wi-Fi go through walls? Let's ask a better engineering question. What actually happens when an electromagnetic wave meets a material? Once we answer that question, everything else starts to make sense. Before we continue, let's do a quick review. Wi-Fi and visible light belong to the same electromagnetic family. They're governed by the same laws of physics. The main difference is where they sit on the electromagnetic spectrum. The biggest difference between them is wavelength. Visible light has a wavelength of about 500 nanometers. A typical Wi-Fi signal at 2.4 gigahertz has a wavelength of about 12 centimeters. That's roughly 200,000 times longer than visible light. That difference certainly matters, but it's still not the complete answer. As wavelength changes, the way a wave interacts with matter also changes. The material hasn't changed, but the wave has. And that's the clue we're looking for. In engineering, we don't just study the wave. We also study the material, because what happens next depends on both. Think of it as a conversation. The wave asks the material how it will respond, and every material gives a different answer. So, we've identified the real question. What actually happens when an electromagnetic wave reaches a wall? Does it simply pass through? Does it bounce back? Or is something more interesting happening in the next section? We'll follow the wave the instant it reaches the wall, and discover that there are 4 possible outcomes. We've learned that Wi-Fi and light are both electromagnetic waves. Now let's zoom in to the exact moment a wave reaches a wall. What happens next? Does it simply pass through? Or does something more interesting happen? The answer is surprisingly elegant. Every time an electromagnetic wave encounters a material, only 4 things can happen. Some energy may bounce back. Some may be absorbed. Some may continue through the material. And some may scatter in different directions. Every interaction is simply a different combination of these 4 possibilities. The first possibility is reflection. Instead of entering the material, the wave bounces back. We see this every day when light reflects from a mirror. Radio waves behave the same way. Metal surfaces, in particular, are excellent reflectors of electromagnetic waves. So, if metal reflects Wi-Fi, could that explain why elevators often have poor reception? We'll come back to that later. When an electromagnetic wave enters a material, the second possibility is absorption. In this case, the wave transfers part of its energy to the material itself. that energy isn't lost. It is converted into heat. Because every material interacts with electromagnetic waves differently, some absorb much more energy than others. A wave is coming. The material has to make 4 decisions: reflect it, absorb it, transmit it, scatter it. The third possibility is transmission. The wave passes through the material. Notice something important. The wave is usually weaker after passing through. Even though it gets through, some of its energy has already been reflected or absorbed along the way. Finally, there's scattering. Instead of moving in one neat direction, the wave is redirected in many different directions. Rough surfaces, tiny particles, or complex structures can all cause scattering. The energy is still there, but it's now spread out. Here's the key idea of today's episode. A wall doesn't simply block a wave, and it doesn't simply let a wave pass. Every electromagnetic wave experiences all 4 processes to different degrees: reflection, absorption, transmission, and scattering. The only question is, how much of each occurs? That is what determines whether Wi-Fi reaches the next room, or whether visible light stops at the wall. To understand why Wi-Fi and visible light behave differently, we need to look inside the wall itself. Not at the bricks, not at the paint, but at the tiny atoms and molecules that make up the material. This is where the real story begins. Every material is made of atoms, and every atom contains electrically charged particles. When an electromagnetic wave arrives, its electric field pushes and pulls on these charges. In other words, the wave doesn't just hit the wall. It interacts with billions upon billions of tiny electric charges. Here's the key difference. Both visible light and Wi-Fi are electromagnetic waves, but they oscillate at very different speeds. Think of it as how fast the electric and magnetic fields flip back and forth. Visible light changes direction hundreds of trillions of times every second. Wi-Fi changes direction only a few billion times each second. That means visible light oscillates tens of thousands of times faster than Wi-Fi. Because of this enormous difference, the electrons inside materials simply can't respond to both waves in the same way. And that one difference completely changes how each wave travels through matter. In many building materials, visible light interacts very strongly with the electrons. Much of the light is either reflected or absorbed. That's why a wall appears solid to our eyes. Very little visible light makes it all the way through. So, the wall isn't trying to stop light. It's simply responding strongly to it. Drywall, wood, and many plastics respond quite differently to Wi-Fi frequencies. They still reflect some energy. They still absorb some energy. But a useful portion continues through the material. That's why your Wi-Fi can often reach the next room. At Wi-Fi frequencies, many common building materials interact less strongly with the wave than they do with visible light, allowing a useful portion of the energy to be transmitted. Of course, not all walls affect Wi-Fi the same way. Some materials are almost invisible to the signal, while others act like major obstacles. Drywall usually lets Wi-Fi pass through quite easily. Brick absorbs and scatters more of the signal. Reinforced concrete weakens it even further. And metal can block Wi-Fi almost completely. So, when it comes to wireless signals, it's not just about the wave itself. The material it encounters is just as important. But water is a special case. Every water molecule behaves like a tiny magnet with a positive and a negative side, an electric dipole. As microwave waves rapidly reverse direction, the molecules keep twisting back and forth, trying to follow the changing electric field. That relentless motion turns electromagnetic energy into heat. It's the very same physics that heats your food inside a microwave oven. Now we can answer the question we started with. A wave doesn't decide the outcome by itself. Neither does the material. What matters is the interaction between them. That single interaction determines whether the wave passes through, gets absorbed, reflects away, or is stopped completely. And that's how engineers understand the behavior of electromagnetic waves. This is the big idea I'd like you to remember. Materials aren't simply transparent or opaque. They interact differently with different electromagnetic waves. Change the wave, and the interaction changes. Change the material, and the interaction changes again. Hidden beneath the painted surface, billions of tiny electric charges are constantly responding to invisible electromagnetic fields. Their collective behavior determines whether a signal is reflected, absorbed, or allowed to continue its journey. Once you understand that, countless everyday technologies begin to make much more sense. If that's true, why can we see through glass, but Wi-Fi becomes weaker? Let's explore some everyday examples. We've just taken a journey inside the wall. Now let's return to everyday life. Once you understand how waves interact with materials, you'll start seeing familiar objects in a completely different way. Let's start with something we see every day: glass. Visible light passes through glass with very little loss. That's why a window looks transparent, allowing us to clearly see what's on the other side. Wi-Fi signals can also travel through ordinary glass, but unlike visible light, they're affected a little more. A small portion is reflected, another small portion is absorbed, while most of the signal continues through. Same material, different electromagnetic waves, different interactions. So, glass isn't simply transparent. It's transparent to some waves, but not equally transparent to all. Now, consider an elevator. As soon as the doors close, your phone often loses signal. Why? Because metal reflects electromagnetic waves extremely well. Very little of the signal can penetrate the metal enclosure. Your phone is almost inside a giant reflective box. Here's one of the cleverest engineering designs you'll find in your kitchen. The metal mesh on the microwave oven door has tiny holes. Those holes are much larger than the wavelength of visible light. So light passes through easily, but they're much smaller than microwave wavelengths. So the microwaves are reflected back inside the oven. That's why you can safely watch your food cooking while the microwave energy stays inside. The same door, two completely different outcomes. Not because the door changed, but because the wave changed. Trees can also weaken wireless signals, but not simply because they're physical obstacles. The real reason is water. Leaves and branches contain a large amount of moisture. And as we learned earlier, water absorbs microwave energy much more effectively than dry air. As the signal passes through dense vegetation, part of its energy is gradually absorbed, leaving a weaker signal on the other side. That's why wireless connections often perform worse when they have to travel through thick trees or dense forests. Whether we're talking about glass, metal, concrete, or trees, the same fundamental principle applies. Electromagnetic waves don't interact with every material in the same way. Some materials reflect them, some absorb them, and others allow them to pass through. Once you understand this simple idea, countless everyday technologies, from Wi-Fi and mobile networks to radar and microwave ovens, suddenly become much easier to understand. Today, we discovered that Wi-Fi and visible light belong to the same electromagnetic family. We learned that every time a wave meets a material, four things can happen: reflection, absorption, transmission, and scattering. And most importantly, we learned that the outcome depends on both the wave and the material. The next time your Wi-Fi reaches another room, or sunlight shines through a window, remember what's happening beneath the surface. Billions of tiny electric charges are quietly responding to invisible electromagnetic waves, shaping the technology we use every day. Once you learn to see that invisible world, you'll never look at everyday objects in quite the same way again. If Wi-Fi can pass through walls, why doesn't it travel forever? Why does the signal become weaker and weaker as you move farther away? Physics isn't just something hidden in textbooks. It's happening around you every second of every day. Once you learn to see the invisible world, you'll discover that ordinary objects are doing extraordinary things. In the next episode, we'll uncover one of the most important ideas in wireless engineering: why electromagnetic waves lose strength with distance. I'll see you in the next episode.